everyone. Good morning, good afternoon. Welcome to our webinar number 12 on pore pressure prediction with TemisFlow. So, welcome. As I just said, we are happy to be with you today for this presentation. We hope you'll find it interesting and useful. So, if you've been following our webinars, you might know us already, but my name is Marika. I will moderate this session. And your main speaker is Alcide Thébault, who is our TemisFlow champion. He's been involved in the development of the software for many years now. So just before we get into the subject, a few guidelines for the meeting. So you are all automatically muted. If you have questions during the presentation, you can use the questions panel that is available at right-hand side. We will try to answer all the questions during the presentation. If we cannot, we'll get back to you afterwards by email. There is also a polls tab in which I will ask you questions during the meeting. So don't forget to give it a look, to have a look. And finally, the full meeting is recorded. So we will put the video in a few days on our YouTube channel and we will notify you when ready. So thank you all. I will now let Alcide get started with the presentation. Thank you.
Thank you, Marie, and hello, everyone. So this is the agenda for today. So I will start with some concepts behind pressure simulation in TemisFlow. I will then show you some illustrations and case studies. So two of them, one from the Middle East that will show some complex migration mechanisms, and another one from the Gulf of Mexico, which will show the link between basin modeling up to the generation of synthetic seismic. I will then end the presentation with a pre-drill pressure risk assessment using CougarFlow. And we will finish the session with a Q&A session where you can ask anything you want about this presentation. So let's start with some concepts. So first of all, why is basin modeling good for pore pressure prediction? So they are a great added value as they model the complex interaction between all phenomena. That way, they provide an understanding of the permeability at a regional scale and over time in order to determine the timing and the quantity of overpressure. The basin modeling provides a reconstruction of the paleoflow history. It provides as well a quantification of hydrocarbon migration and an assessment of the reservoir charging through time. It also provides an assessment of entrapment efficiency. With basin modeling, you can estimate the seal capacity and the reservoir quality. And finally, it brings insights for well planning. So for example, the drillability of a target, the mud that you will need to drill, or the casing design. So the main point is that pressure matters, and every basin modeling study should start with a pressure modeling and a calibration phase. So what are the processes that are taken into account in TemisFlow? TemisFlow benefits from a very robust simulator, which has been continuously improved by our researchers at IFPEN to better handle a complex geologic context. So that way it accounts for water flow, compaction, tectonic loading, chemical compaction, diagenetic seals and shell dehydration, hydrocarbon buoyancy, hydrocarbon source, hydraulic fracturing, lateral stress, and potentially more that I forgot to mention here. Before we get into the core of the topic, let's discuss quickly some definitions. So we will talk of hydrostatic pressure when we talk about the water pressure. The lithostatic pressure is the it's the weight of the sediments, and the pore pressure is the pressure within the pore space. When we are below hydrostatic pressure, we call it under pressure. When we are above hydrostatic pressure, we call it overpressure. And finally, the effective stress is the difference between the lithostatic pressure and the pore pressure. So what we first need to define in order to have a proper pressure model within our basin are some good boundary conditions. So we need to define a top condition, which corresponds to the piezometric surface, which means the limit where the pressure is equal to the atmospheric pressure. So that limit is the sea level offshore, and it's the water table level, so the top of the aquifers onshore. There is no bottom condition to define, and by default, the lateral conditions are left open, but it is possible to constrain them if you want to consider the fact that your model is part of a bigger basin. So you can either put some user-defined pressure conditions, which is what is shown right here, where you may have a mountain range on the side of your model that will have an impact on your model, or you can also perform some windowing from a larger and generally coarser model. So you first run a very big model with a coarse grid, and you use that pressure condition to constrain the limits of a much refined local model. So what are the main driving factors? So they are the rock's petrophysical parameters, of course. So you need to properly characterize the rocks that fill your basin. So you will first need to take into account the density, which will represent the sedimentary load through time. The sediment is, yeah, exactly. No, it will represent the sedimentary load through time. You need to define properly as well the porosity of these rocks. So the porosity is the available pore space, and it is defined as the function of the effective stress. So as you can see here, it decreases with depth, with the burial of the rocks through time, and it has a different behavior depending on the lithology. So for example, here you have a higher porosity in general for sands than for shales, and it's a different trend for carbonates as well. The other parameter that needs to be taken into account is the permeability, which drives the water flow and which is usually defined as a function of porosity and specific surface, where the specific surface is the contact that you have between grain per volume of rock. So it's the surface in content per cubic meter. So here, for example, we have the Kozeny-Karman law that defines the permeability with porosity, and here you see the permeability trend for sands or for shales. So these were the main driving factors, but you can of course take some much more advanced phenomena into account when trying to quantify the pore pressure within a basin. So here, let me present to you the diagenetic processes that can be handled within TemisFlow. So we can take into account diagenetic processes on sandstones or shales. So for sandstones, we take into account the quartz cementation, which is this law. So where you will first define a purely mechanic driven pressure curve, and all the chemical aspects will be computed through this equation, where you will have precipitation and cementation of quartz, and that improves the pressure prediction in deep prospects. Second of all, you can also take into account the chemical compaction of shales by taking into account the porosity and permeability reduction with smectite and kaolinite when they turn into halides. So this is modeled thanks to a first order kinetics. So you define the transformation of smectite into halite and kaolinite into halite, which will usually occur around 60 degrees for smectite and 110 degrees for kaolinite. So here, for example, you have the occurrence with depths, and here the effects on overpressure. Then another element that can be very critical at basin scale is the fault effect. So faults may play a critical role on pressure and of course on the migration pathways for the hydrocarbons. So they will act as juxtaposition interfaces. They can also be permeable, impermeable. Their behavior may vary through time, and they can depend on the deformation. So here you will have two ways of handling faults within TemisFlow. Either if you are in a vertical pillar grid, which is the classic approach, the faults will mostly be a transition in lithology. If you take into account when you use the most advanced workflow where you couple ChronosFlow with TemisFlow, you will be able to explicitly take into account the faults into the mesh. So it's a complex mesh, an unstructured mesh, and you will have the perfect representation of the movement of the fault through time through a structural restoration. So here to the left, I will show you an example from central Russia, from the Mesozoic ridge, where we will follow the buildup of pressure within a reservoir through time. So here with burial, you see that the pressure increases and we start having some compartmentalization of the pressure. So some very local buildup of pressures, which are due to the fact that the faults are considered to be impermeable. So all that is controlled by some wells that allow us to calibrate the information in some of these compartments in order to get to the final pressure regime at present day, which will be very important for hydrocarbon migrations and also for drilling risk. Here to the right, we are offshore Canada, and in order to assess the pressure in that purely exploration basin, so where we have almost no control, the wells are within the platform, so we have almost no control within the basin. We tested two scenarios in order to understand the risk with the pressure. So here at the top, the faults are considered to be transparent, which means that their behavior is just due to the juxtaposition of the layers on both sides of the fault. And here we have a totally impermeable behavior. And with time, we actually see quickly a difference of behavior with here a compartment that is way more homogeneous, and here a buildup of pressure with a compartmentalization between the different fault blocks, which translates at present day to quite a different organization of the pressure. So if we wanted to drill, for example, right here, it would be important to know what is the best case and the worst case scenario. So of course, here a more advanced analysis of the fault processes through a shale-gauge ratio approach, for example, could be interesting to discriminate between the two cases. Another element that can be important as well when you handle pore pressure is to take into account the lateral stress. So here, as I have not mentioned yet, but in TemisFlow, the stress is considered to be purely vertical and is mainly related to the sedimentary load, which is, in any case, the main driver for pore pressure. But in certain contexts, it is important to take into account the lateral stress, for example, in compressive settings or when you have some strong salt movements. And that is possible to be done in TemisFlow by defining stress ratio maps through time and space. So the first step will be to understand the stress within the basin. And so that can be done with a third-party software, so geomechanical tools like Kine3D or Codaster that does that really well. So Kine3D 3. And when you use that, and when you have that map defined, when you have understood the stress direction, you can define a ratio maps, which is the ratio of the horizontal stress over the vertical stress or vice versa, in order to know how to increase your vertical stress or decrease your vertical stress in order to take into account the lateral component. And that is taken into account within the calculator, and it will have an impact on porosity, effective stress, and overpressure, of course. So this is, for example, the behavior within one reservoir layer through time without lateral stress, where we keep high porosity, and here with the lateral stress, where the porosity is decreased due to a compressive regime. I mentioned some buildup of pressures, but we also have to take into account the release of pressure through time. So what are the main release mechanisms that we can take into account? The first one is just a relaxation of the system through time. So if you have a low sedimentation rate at a certain moment, that will just allow the system to equilibrate, and you will lose some pressure. It can also be linked to hydraulic fracturing. So when the pore pressure gets pretty high, it may get over the fracturing threshold of the rock. And in that case, the permeability will increase and the porosity, the pressure will decrease due to that increase of permeability. So this is some natural fracturing of the rocks. And finally, it can also be due to a stress release after unloading or an erosion phase. So usually with time, you have the burial of your rocks. So the porosity decreases following the porosity stress curve that I mentioned before. But with an erosion, you remove some of the sedimentary load, and the porosity will increase due to the elastic rebound, due to the elastic properties of the rock. So you regain a bit of porosity, but not exactly the porosity that you had lost due to the burial before. And that will, of course, that porosity increase will provide a decrease of pressure. So here we have mentioned the main effects on pressure linked to water and the rocks, but we also need to consider the hydrocarbons. So of course, this is one of the major added value of basin modeling, is that it allows to integrate the hydrocarbon phase within the system, which will have an impact on the pressure regime. And the pressure regime will also drive the migration and accumulation of the hydrocarbons. So in TemisFlow, in order to properly represent the migration of the hydrocarbons, we consider a polyphasic Darcy's law, which relates the flow to different driving forces. So the main one is the buoyancy, just the fact that the density of hydrocarbon is lower than the density of water means that the hydrocarbons tend to go up. The second driving force is the capillarity of the rocks. So it will make it easier or harder, actually usually harder, for hydrocarbon to enter within a rock. And the other parameter that needs to be integrated is the gradient of pressure, so the pore pressure, which through hydrodynamism processes or with a high water flow will push and move the hydrocarbons into a certain direction. And sometimes that force can be even stronger than the other ones, as we will see in some examples. And in addition to these forces, there are, of course, the intrinsic properties of the rocks that need to be taken into account. The permeability that I have mentioned before, the relative permeability, so the way each fluid moves into the pore space, and the viscosity of each phase. So, as I said, the hydrocarbons have to be taken into account as they have an impact on pressure. So here is an example to illustrate that aspect with a very simple model where we have a reservoir layer and a seal on top. This would be the trend of pressure that we should expect within that sedimentary column. And if we integrate hydrocarbon within the system, so here we see if we consider a very high hydrocarbon saturation within this reservoir, we should expect an increase of pressure, so some overpressure within the reservoir body. That needs to be considered if we want to drill that prospect. So this was the impact of hydrocarbon on the pressure, but as I said as well, the pressure will have an impact on the hydrocarbon migration. And here is an example where the Darcy law make it possible to model the impact of the pressure gradient on the hydrocarbon migration and trapping. And so, for example, right here, it would be possible to define a lateral fluid flow through time and space to define an active aquifer. So this is a very interesting case from the Middle East, where due to a strong erosion phase, this reservoir right here gets connected to the surface, and we have a flow of water that gets into the reservoir and pushes the hydrocarbons. So this is the case without hydrodynamism, and this is the case where hydrodynamism, which brings some hydrocarbon flushing and an all-water contact tilting, which is very important and very nice to represent, as it allows to properly characterize the accumulation that is not located where we would expect it, which means at the top of the structure right here. Finally, with some complex settings, we can have sometimes as well a pressure gradient that is no longer upwards, but is downward and will push the hydrocarbon downward as well. So in some areas, the modeling certain accumulations will require a very precise pore pressure modeling and an accurate algorithm to properly represent the hydrocarbon migration. So this is, for example, a complex case where you see here that the mesh is actually an unstructured mesh, not only a simple vertical mesh. So this was done coupling TemisFlow with CougarFlow. And here you will see that with the hydrocarbon migration, so within that reservoir, we have, because here the hydrocarbon is blocked against that block right here with a high capillary pressure, so a low permeability, we start having some downward migration into this reservoir body right here. So here the hydrocarbons come from the top. So we can see it a little bit with the vectors that are here lateral, here very slow downward migration, and here a downward migration, which is this way. So this is due to the pore pressure field, which is actually higher here than down there. So you see here that you have a downward gradient, which is linked to the capillary pressure. As I said, here the hydrocarbons cannot go here, and it pushes the hydrocarbons down. So with time, what happens afterwards is that this accumulation goes up here, and we end up with a strong accumulation here that is first linked to a downward migration right there. So this is very interesting and important to be able to model as well. So to conclude that theoretical section, these are all the phenomena that are taken into account within TemisFlow. Everything is connected, everything is linked. In order to drive the migration, you need to have a nice pore pressure field, but the hydrocarbon migration will impact the pressure in return. Everything is connected, and everything has to be taken into account to have final result that is valid and correct. So in order to illustrate that, I will show you two cases. The first one being a case on downward migration in the Middle East. So just to actually show you another real case example from what I just explained. So here the study context, what I will present was part of a bigger study, which objectives were to characterize properly the source rock, to have a nice pore pressure prediction, and to also have a comprehensive play fairway analysis, which includes the hydrocarbon masses estimation. So in that area, the challenge was to understand the presence of hydrocarbons in a deep reservoir, which is here the Marat reservoir, without any known source rocks underneath. So just to explain in more details the context, you have a very strong seal, which is the Godnia salt. Right underneath the seal, you have a good source rock. Underneath the source rock, you have some tight reservoirs which show some hydrocarbons. Here you have another seal, the Daruma seal, and underneath that seal, you have another reservoir which is 30 to 150 meters, depending on the area of the basin, below the source rock. And in this reservoir that has been drilled, there are some nice accumulations, and we would like to understand where those accumulations come from, because either there is a source rock below, either it is from that source rock, but that would require a very, very long downward migration. So the reason for it is that the pressure field actually suggests the existence of a slow water flow from the source rock into the reservoir, which converge laterally towards some salt windows. So here what happens is that within the salt, you have some salt windows that release the pressure, that create a very strong pressure gradient upwards here. Because these reservoirs are pretty tight, the lateral flow is not very possible. Here in that main reservoir, you have a strong lateral flow towards these windows, and that lateral flow creates a depletion of pressure underneath the source rocks, which creates a strong downward gradient of pressure, which helps the hydrocarbon migrate downwards. So here you have a first downward migration and then the lateral migration into the into the marat. So how is that represented by the basin modeling? So here is a 2D section to represent that, where we find here the Godnia salt, the Najma source rock, the tight, another seal right here, and the Marat reservoir down here. So this is the pressure field that results from the modeling. So here you see some strong overpressures underneath the salt, and you see some lateral water flows that converge to that upward water flow, and that creates this plume of pressure in the impervious carbonates above the salt. So here you see that gradient of pressure that is created laterally underneath the salt and upwards through the salt windows. And that can actually be observed on seismic, where we actually see within the impedance a signature of the overpressure that can validate that result. So in terms of hydrocarbon migration, this is what we obtain. So the hydrocarbons migrate from the source rock that is here. You can see that we see some lateral migration a little bit here, but also some accumulations underneath that migrate laterally and upwards on top of the salt. So we identify 3 types of accumulations. 2 accumulations here in 2 fields, I would say, in the Cretaceous area that are sourced by the salt windows. Another field here, which is in the middle Marat, and here some fields that are within the middle and lower Marat. So here you see that from the source rock, we have some hydrocarbons that are here present here, even 100 to 500 meters below the source rock. And here in that model, we didn't define any source rocks underneath the reservoirs. The only major source rock is this one. Another interesting fact is that the hydrocarbon signature of the accumulations that were drilled underneath the source rock matches the signature of the organic matter within the source rock, which means that this scenario explains why we can find some hydrocarbons. The signature is the same, so this should validate the scenario. Second case study is the pore pressure prediction in the Gulf of Mexico. So this project was done through a consortium organized by the SEG. It was called the SEAM project, as the objective was to deliver a model and the associated synthetic, the objective was to, through the delivery of a model and the associated synthetic seismic datasets, to investigate and improve the overpressure estimation. So what the SEG wanted to do was to test the various solutions that were available on the market through a 2D and a 3D approach, and see which one was bringing the best pore pressure modeling. So the characteristic of that model, of that SEAM section, is that we have an abundance of shale. We have a very young mini basin right here with a very high sedimentation rate, and we have a presence of a complex salt geometry, which requires a complex structural evolution. So this is actually the structural restoration that was proposed by Beicip. So we first start with the autochthonous salt that grows through diapirs. We have a canopy advance in the late Miocene, which is followed by the mini basin emplacements. And then we have a welding out and the shaping of the canopy at present day. So here you see the very high shale content. And here the facies definition was done with V-shale cutoffs that allowed us to describe the presence of sand and shale, which properties were just defined by the default library available within TemisFlow. So this is the result of the default simulation with the default parameters, where here we see the effective stress distribution. So we see that we observe increasing effective stress with depth, with here the high loading that creates some nice overpressures here. We have also here a very low effective stress at underneath the salt, which represents the salt effect, and some strong overpressures at actually a strong effective stress, which means that here we actually have less overpressure in that area. So here, this is the salt effect that we have right here. And here we can observe as well a centroid effect, which means that within the reservoir bodies, we can see that the pressure field the pressure is connected, that we have that means that we have the same pressure regime within the whole reservoir body. So this can be better observed here with a filtering on the of the overpressure on the reservoirs. So where you see that in each reservoir body, the pressure is very similar, which means that we properly represent the connection of pressure within these continuous reservoirs. Then we tested as well the impact of diagenesis, so smectite to halite transformation, which is related to the temperature. So here you see the temperature regime within the section, which is linked to the presence of the salt. So the salt tends to cool down the temperature underneath the salt, and it also is increased by the by the strong burial right here. And here you have the impact of elitization, which occurs usually within a range of 60 to 100 degrees. So here is the percentage of elitization that is observed. So this is the difference in terms of effective stress that can be observed. So this is the reference case without elitization, and this is the case with elitization, where we observe right here a much lower effective stress, which means that we have a much higher overpressure underneath the salt due to the reduction of permeability through the elitization process. Same thing actually pretty much everywhere where the effective stress decreases. Finally, using that very nice pressure representation, we computed some seismic velocities. So in order to derive the seismic velocities from the pressure field, we used a Wernicke and Kashanov approach. So they came up with a relationship between the rock elastic properties and the pore pressure to derive the seismic velocities. So this is the result in terms of S wave, P waves, and Poisson ratio. So this is very nice in order to improve the velocity model and have a better representation of the interpreted seismic horizons at present day, or it can also be a way to validate your basin model. After doing the work in 2D, we did it as well in 3D. So the workflow was exactly the same. The model was a very high resolution model in 3D. So 33 million cells. So one of the biggest I've seen. So with a very low, high cell resolution. So very low size for the cells, 75 meters, 135 layers. And here as well, we came up with several scenarios depending on the elitization effect in order to have the same workflow in 3D at basin scale. So that concludes the case presentations, and I will finish my talk with showing you an uncertainty management to assess the drilling risk. So using that SEAM project. So here the idea is to estimate the drilling risk for two potential targets, one located underneath the salt and another one, which would be right here, these reservoirs within that small anticline. So here the objective is to understand the driving factors for the overpressure and to identify the best case scenario, so the P90, and the worst case scenario for the drilling. So what would be the pressure regime that we can, the best pressure regime and the worst pressure regime we can expect in that area. So in order to do that, we will use a response surface approach, which is done by integrating CougarFlow with TemisFlow. So CougarFlow is part of Beicip-Franlab solutions and allows to understand uncertainties and understand the risk associated to the model. So the idea is to use a response surface that is built from a limited number of simulations in order to drastically reduce the number of simulations that are needed to understand the variability of the model without compromising the result quality. So what happens is you select your uncertain parameters, so the inputs that you want to vary. From that variation, the software will give you an experimental design, which is a limited number of simulations that need to be launched in order to properly characterize the uncertainty space. You launch these simulations, and from the results of these simulations, you build a response surface that will mimic the calculator behavior. And on that surface, you can sample 10,000, 100,000 simulations to have a quantified vision of the variability of the model in just a few seconds. And that will give you access to a sensitivity analysis and a risk analysis. So here in that case, the parameters that were defined as uncertain are the permeability of the sand and the shales. So this is done through the definition of their specific surface that varies by an order of 20%. And we also made vary the diagenetic effect, which varies by 15%. So where here we made vary the impact of the elitization on the variation of the specific surface. So through the elitization process, the specific surface will increase less, so decrease more or less the permeability. So once we have defined that range, we launch here the 12 simulations that are needed. And here you see the results of the 12 simulations extracted at well 2 in order to have the variability of the model within that well. And from these 12 simulations, we computed one response surface per stratigraphic unit in order to know the variability in each sequence. So that is done automatically directly by the software in just a few minutes. The final results are the following. So this is for the two pseudo wells. So you see that this is actually the sensitivity analysis where you see for each depth, the parameters that are the most impactful. So we see here that it's mostly the shale. So at the top, the shale permeability, and at the bottom, the shale diagenesis that is the most impactful, which means that these are the main drivers for the pore pressure within the system. So it means that the shale diagenetic effect should be characterized at best in order to have the best pressure estimation within this basin. And finally, this is here the risk analysis. So that means the variability of the overpressure. So for the first well, you see right here that underneath the salt, we have a jump of overpressure. And then here the P90, so the best case scenario, the P10, which is the worst case scenario, so 10% chances to be above that, and the P50, which is I would say we have 50% chances of being above it. So for well 1, here for well 2, where we do not have any salt, but we have a small increase of pressure through time. And what we see is that for the well 1, we have actually a low risk in the sense that the variability of the overpressure that can be expected in that area is very small. So we only have a 3 megapascal delta. So of course, we have to expect a very strong overpressure shift, but that overpressure is pretty well characterized and pretty well defined. When here within our target, the risk is average. We see that we have a 7 megapascal difference between the worst case and the best case, the best case and the worst case scenario, which means that we may need to adapt the mud weight or the casing while drilling and expect for the worst, I would say. But the good thing with that approach as well is that once you know the trend, you can actually extrapolate and use the simulation that was the closest to your trend in order to know what to expect next when drilling. So finally, before the Q&A break, I will just add one thing that is missing within that analysis, which is the presence of hydrocarbon. So that would be the next step, because of course, if we consider these areas to be targets, that means we expect them to be filled with hydrocarbons, and that hydrocarbon presence will bring more overpressure within these reservoirs. So that means that by taking it into account, we would have a better estimation of the overpressure to get into the reservoirs, and a better assessment of the drilling risk. So this concludes the presentation. I don't know, Marie, if we have some questions that we can answer before finishing the meeting.
Yes, perfect timing. Thank you. We still have a few minutes to go. We have some questions. So let me ask you the first one related to fault and fault properties and impact on pressure, of course. So it's three questions in one. So I'll go with the first one. Can you assign a variation of fault properties along the fault to demonstrate the variation of sealing capacity along a particular fault?
So yes, the answer is yes. In the two approaches, that would be possible.
How to account for the dynamic behavior of the fault sealing capacity through time?
So you can, so that would be done in two ways. The first one is through your reconstruction of the model. So because of the fault movement, of course, the impact of the fault will be different. So that is done through thickness variations in the classical approach, or through your structural restoration in the advanced approach, I would say. And you can also, the same way as your properties can vary along the fault, they can also vary through time. So for example, if you want to take into account the cementation of your fault or reactivation of the fault, which makes it more permeable, that would be possible as well.
Third question, can this account for the SGR clay smear in the fault plane?
Can that take into account what? Sorry,
the shell gauge ratio in the fault plane.
Yes, actually, that would be, if you have a shell gauge ratio analysis, that would be the best way to define that. So know that in the software, what you need to enter is a permeability effect and a capillary pressure effect. So that means you need to translate your shell gauge ratio analysis into that, but it's a simple translation that can be integrated, and the variability at present day or through time can come from that analysis.
Thanks. Next question. In 1D pore pressure prediction, we have to consider whether sand layers are in pressure equilibrium with shale. Does TemisFlow take into account on whether they are in equilibrium or not?
I would say in TemisFlow, there is no assumption, because we take into account the overall system. Because usually for pore pressure prediction, it's better to do it either in 2D or even better in 3D, because the effect of pressure in one area can be due to the presence of another phenomena somewhere else. So here what we do is we define the rock properties, we define the evolution of the basin through time, and then everything is integrated in order to obtain the evolution of the pressure regime through time. So there is no assumption that are done. So the equilibrium will be obtained or not just due to the evolution of your basin through time, I would say.
Do we have anything for modeling the fracture gradient as well, since it is needed for well design?
So not really, no, because actually the fracture gradient is more an input data in TemisFlow, because this is more linked to a rheologic analysis. So it's more a petrophysical property of the rock. So that's unfortunately, no, you can take it into account, which means, as I showed you, that when the pore pressure gets over your factoring threshold, it will crack the rock, but it is not an output of the software.
Absolutely. All right, that's it. Perfect timing. It's been 45 minutes we are together. So if you don't have other questions, I think we will be good for today. If you have further questions, feel free to write to us. We'll be happy to answer. But I assume, so it's still on the fracture gradient, Elcid. But I assume there is a calculator that we can create to generate the fracture gradient in TemisFlow. There is always room for improvement in our technology, and of course we can probably work on something about it. So we'll have to discuss it with our R&D team. Why not, indeed, improve that aspect in the software. So thanks again, everyone. We hope you enjoyed the meeting. There are 3 questions actually to answer in the polls tab. So if you can have a look before you go, that would be nice. And otherwise, well, we wish you a good end of day or good night for some of you. And we look forward to see you again next time. Thank you.
All right. Thank you.
Thanks, Elcid.